From the simplest light switch on your wall all the way to the massive, sprawling data centers that power our digital lives, there is this unseen engine at work. We're talking about the electromechanical sector. It's the physical backbone of our entire modern world, and right now, it is going through one of the biggest transformations in industrial history.
So let's get into it. Here's our game plan. First, we're going to wrap our heads around the sheer scale of this industry. Then, we'll look at the cracks that are starting to show in its very foundation. We'll dive into the material shortages that are squeezing supply chains and see how AI is, believe it or not, coming to the rescue. After that, we'll check out how this whole shift is impacting global competition, and finally, we'll look ahead at what the future has in store.
All right, first up, let's try to get a handle on just how massive this market really is. We are talking about the nuts and bolts of the entire energy world here.
Get this, as of 2023, the global market for all this electrical equipment was already valued at over $1.5 trillion, and it is not slowing down. Projections see it blowing past $2 trillion by 2030. And this isn't just because we want more stuff, it's because we are in the middle of a fundamental rebuild of our entire energy system.
Now, what's really fascinating here is how this growth is happening pretty much across the board. You see this huge expansion in massive, grid-level hardware like switchgear, all driven by the need to modernize. But at the exact same time, tiny little components like relays and sensors are also booming, thanks to everything from factory automation to medical tech. It's a total system overhaul, from the biggest parts to the smallest.
So, what's behind all this explosive growth? Well, it really boils down to three powerful megatrends. First, deep electrification. We're putting everything on the grid, our cars, our home heating, you name it. Second, renewable energy. We're moving away from a few giant power plants to millions of solar panels and wind turbines. And third, the data economy. AI and cloud computing have created this insatiable new mega customer, the data center, that needs just a staggering amount of power.
But, and this is a big but, all of this massive new demand exposes a huge problem. We're trying to put all this new world tech onto an old world infrastructure that is, to put it nicely, old and fragile. Just let that sink in for a second. In Europe, a huge chunk of the grid was built for a completely different time. This isn't just a simple maintenance issue. These aging systems are a serious bottleneck. They are physically incapable of handling the demands of renewables and the continent's big climate goals.
And the price tag to fix all this? It's absolutely staggering. Europe needs to pour in nearly 600 billion euros just by 2030. And we're not just talking about replacing old wires here. This is about making the entire grid smart, resilient, flexible, and efficient.
So, here's the crucial point. Europe's vision goes way beyond a simple upgrade. What they're aiming for is a system of systems. The idea is to seamlessly weave the electricity grid together with hydrogen, heating, and transportation, creating one giant, intelligent, flexible energy network. Okay, now let's hop across the pond. The US grid, often called the world's largest machine, it faces a different main threat. For the US, the big challenge is resilience. Climate-fueled events like hurricanes, wildfires, and ice storms are causing blackouts way more often than in other developed nations. And this table just brilliantly illustrates the two very different paths being taken. Europe is all in on integration, creating a unified digital twin of its entire grid. Meanwhile, the US is using its big infrastructure bills to harden the grid against extreme weather and to seriously boost its domestic transmission capacity.
But here's the thing. Whether you're building for integration like Europe or for resilience like the US, you eventually run headfirst into another, more fundamental problem: the physical limits of our supply chains.
That's the question the entire industry is asking right now. We are smack in the middle of a global supply chain crisis for the most basic building blocks of the electrical world, from the special steel and transformers to the copper in our cables.
This bottleneck is hitting transformers especially hard. You see, steelmakers are finding it way more profitable to make steel for EV motors. This has totally choked the supply of the specialized steel needed for transformers, and the result? Wait times for these absolutely critical components have just ballooned from about 1 year to as long as 4 years. So this material squeeze is forcing innovation, and it's kicking off what you could call a conductor war. For ages, copper has been the gold standard, but now, with huge supply shortages predicted and costs going through the roof, manufacturers are looking seriously at aluminum. Sure, it's not quite as conductive, but it's drastically lighter and cheaper, which makes it a really powerful alternative if you can engineer it right.
Just when these physical challenges, the aging infrastructure, the material shortages, seem almost impossible to solve, a powerful digital solution is emerging that could change the game entirely.
Say hello to generative design. Instead of an engineer tweaking a design over and over, they now just tell an AI the goals, make it lighter, make it more efficient, and the rules it has to follow. The AI then simulates literally thousands of potential designs to find the absolute best physical shape. And it's often a shape a human would have never, ever thought of.
And the results are just stunning. In one case, an AI-driven design process for an electric motor cut its weight by 47%, while also increasing its torque. It's not just making things faster, it's creating physically superior products.
But the impact of AI goes way beyond just designing parts. We are now seeing the grid itself learning to think. Think about it. The sheer complexity of managing millions of inputs from solar panels, batteries, and EV chargers is way beyond what any human team can handle. AI is what's making an autonomous grid possible.
And a great real-world example of this is Siemens' GridScale X platform. It basically runs on a digital replica, a digital twin of the actual grid, and it analyzes tons of data to predict problems days in advance. It can proactively manage voltage spikes or optimize energy loads to squeeze every last drop of performance out of the existing hardware. This often means you can avoid having to do expensive physical upgrades in the first place.
Now, this massive technological shift is not happening in a vacuum. Of course not. It's completely redrawing the map of global supply chains and kicking off some really intense geopolitical competition.
Let's take a look at Turkey, which finds itself at this fascinating crossroads. On one hand, European companies are desperate to nearshore their supply chains, basically move them closer to home and away from Asia. Turkey is a prime candidate for this. But there's a huge catch. It's a new EU policy called the Carbon Border Adjustment Mechanism, or CBAM. You can just think of it as a carbon tax at the border. For Turkish manufacturers, this is a total game changer. They have to pivot, and pivot fast, to green materials like green steel and green aluminum, or they risk getting priced right out of their most important market.
Okay, so after looking at the incredible scale, the huge challenges, and the emerging solutions, what's the big takeaway here? Where is this whole electromechanical world really headed?
It really all comes down to this. The future isn't just about building more stuff. The companies and countries that win in this new era will be the ones that can brilliantly fuse the physical and the digital. They're going to be the ones that fortify their infrastructure with AI, innovate their way around material shortages, and make sustainability the absolute core of their entire strategy.
And all of this leaves us with one final and really critical question to think about. We are betting our future on digital intelligence, on AI, to solve our physical problems. But the very AI we're relying on has a colossal and rapidly growing physical energy footprint of its own. So what happens when the demands of our digital savior begin to outstrip the capacity of the physical world it was supposed to be saving?